Right. Hi, welcome to Starlark Debugger Deep Dive. My name's Paul. I'm the founder of StackBuild, and I've written a number of Starlark rule sets, such as StackB Rules Proto. I help maintain some of the core rule sets, such as Rules Docker, and I've written a number of tools along the way, including a Bazel build user interface, Starlark language server, and now a debugger that I'd like to share with you today. So let's get started. This is an overview of what I'll talk about. So we'll talk about what you can do with it, um, who the target audience is, what the architecture looks like. We'll take a peek at some of the server flags and look inside the server implementation to get a better sense of what it's doing. We'll peek at the protocol a bit and some of the message types. And then we'll take a look at the debug client, both as a standalone CLI and in the IDE. So since we're talking about Starlark, it's worth mentioning there are three implementations. The one written in Java, which is inside the Bazel build code base. There's also a mature Go implementation, as well as a Rust implementation, whose maintainership has recently transitioned to Facebook. All three have their own debugging capabilities, but we'll just be looking at the one inside Bazel today. So the debugger experience can be a little frustrating. So it's not something you're likely to recommend to your average developer who's just trying to figure out why their build is broken on CI. Rather, it's more suitable to rule set authors or core Bazel developers in an organization that are trying to get a better understanding of some Starlark behavior. The debug experience starts with the long-running Bazel server, which advertises the debug protocol over port 7300, and they exchange asynchronously messages according to the Starlark debugging protocol format. And optionally, in this architecture, we also have the IDE connecting to the client over a different protocol, so-called DAP protocol, which is going to act as a debug adapter. So the core debug server is implemented inside this Starlark debug package. This is a fairly simple Java package that wraps and hooks into this core Starlark engine. If you didn't know already, you can check out the Bazel code base, and with a single Bazel run command, you can drop into a Starlark REPL, and I definitely recommend doing that sometime. So let's take a look at the flags that you'll want to be using. The first one is this experimental Starlark debug flag. This is the only one that's required. And when this is invoked, the server will pause, waiting for a client to attach. Optionally, you can customize the port, but usually the default works fine. And then there's this flag to enable verbose logging. I would almost always recommend this, but occasionally you'll hit a complex variable, and the attempt to serialize that to the client will just really halt a debug session. So use it at first, but you probably don't need it going forward. The TLDR on this slide is that the Starlark debugger module is only active with the build command. So the flags will really have no effect with query or test, for example. And if I had to distill the debugger implementation into one spot, this might be it. And essentially, when the debugger is active, anytime a Starlark thread is about to arrive at some particular location, there's a callback, and the debug implementation gets an opportunity to pause the thread or do additional operations at that time. Okay, to summarize then, we have the experimental Starlark debug flag in conjunction with the build command that allows you to do thread operations at the statement level. Okay, let's peek at the protocol a bit. This client request implementation kind of gives you a sense of the types of messages and what you can do with things. So you can list stack frames, you can set breakpoints, you can continue, pause, step through threads, and then there's evaluate and get children, which I'll address separately. So when a client issues an evaluate request, it's essentially sending a raw Starlark string, and that gets installed and evaluated into that particular thread with its current state. Unfortunately, the way the debugger stands right now, evaluation always occurs in the global file scope. So that's less useful because you can't really see what's happening with variables inside of a function or inside some, if statement. So that is usually IDE hovers are powered with evaluate, and also conditional breakpoints don't work. So there's some limitations, but as long as you're aware of them, it's okay. The getChildren API is used to facilitate a drill down approach to complex objects. So if an object has internal structure, it's given an ID, and that ID is then used for a subsequent API call to retrieve the child nodes of that object. In an IDE, this is usually represented as like an expandable tree item view, for example. And this slide gives you a sense of the types of objects which do advertise internal structure. A notable exception to this is the provider object, which is unfortunate because provider is probably one of the more interesting objects you might want to explore, but just as long as you're aware of it. Okay, let's shift gears a little bit and let's talk about the client implementations. So the reference implementation is Bazel build VSCode Bazel, which is written by Tony Olivato and colleagues. Laurent Lebrun has also written a Go implementation. And this one, based on the Bazel tool, is based off Delve, which is a popular debugger for Go. Also a shout out to Torgil Svensson, who presented at the last build meetup about one written in Python. You can find his talk online. So this is a subcommand of this Bazel tool. You can curl and download this and use it however you like. If you're using it at scale within a large organization, we ask that you get it properly supported. But otherwise, it's the Bazel debug tool. And what happens when you invoke that is it'll drop into the CLI and attempt to attach to a server. And when I'm running this, I typically like to have two terminals open, one for the server and one for the client that I can see at the same time. And so that's what we'll look at right now. So here we're running the server. It's now waiting to connect. Bazel debug, now it's connected. Okay, it's paused at line 1 of this thing called default workspace. We'll look at what that is in just a second. And we can use commands like T for listing threads, or F for listing stack frames, L for local variables, G for global variables, of which there aren't any right now. We'll look at those in a minute. So let's digress just for a second. What is this curious thing called the /default workspace? Well, when Bazel parses your workspace file, what it actually does is it prepends content before and after to install built-in workspaces like Bazel tools, which can't be overridden, and then things like the local JDK and any number of remote JDKs you've probably accidentally downloaded at some point or another. There is a subcommand called default workspace content, which will prepare these files. It makes the debugging experience just a little nicer, but it's optional. All right, well, let's look at something a little bit more interesting. And specifically, let's use the debugger to ask, how is it that something like rules Go can compile two binaries on different platforms during the same Bazel build command? So here I'm building a command called gencopy. It doesn't really matter for the demo what it does, but when I build it, as expected, I get a binary that's compatible with the host platform, in this case, Mac. If I add the -- platforms equals label pointing to some platforms rule, then I get a cross-compiled binary that's compatible with Linux. This in itself is rather remarkable, but what if I don't want to compile everything for the same platform all during one build command? And what I can do in this case is remove the -- platforms flag and use the goose and gorch, apparently that's how they're called, flags, and move those into the Go binary itself. And then when I build this, I get one binary that's cross-compiled, one that's not. So this is kind of crazy because it's as though I've invoked different command line flags for different parts of the build graph. So this is called a transition, and it has a special rule called transition. And there's a transition implementation, like a rule implementation. And so let's look at that using the debugger. But I don't really know even where to start with this, so I'm going to use a different tool, which is a code search tool, to kind of narrow it down. And in this slide, what I'm going to do is build a search index based on a Bazel query, and then use a search command to look inside that Bazel query. So it's kind of like live grep for Bazel queries. So here I've used the build files operator. And so this builds a search index based on all the transitive BZL and build files for that Go binary. And I can search within it. And I've searched for the string GOOS. It only has a few hits, which is nice. And the file called transition BZL looks like the most interesting. So I've opened that up and I've looked through it a little bit and I have a sense of where I want to put my breakpoint. And so we'll go ahead and do that now. Again, I'm going to have two terminals open, one for the server and one for the client. So this is what that looks like. So we'll go ahead and launch our server. Now it's waiting to attach. Debug is now attached. It's in transition BZL at the start of the file. I'm setting a breakpoint in line 125. It's going to show me where my breakpoint is. And then what I can do is then inspect local no, I'm continuing. So I'm hit the breakpoint at line 125. I can inspect local variables. Here, there's a dictionary called settings, which actually has a mapping between the platforms flag and this host platform. And we're going to watch that update. So what we're going to do is step SSS as we go through the code here, and we're going to drop into this if statement about GOOS. And what we're going to see is this platform string being constructed and the settings dictionary updated. We can re-inspect our variables, local variables. Here the platform is indeed changed to Linux AMD 64, and we've updated the dictionary. Now this settings dictionary is the return value for the transition rule implementation, and that is actually what a transition is in Bazel. So you're just updating the settings dictionary based on some conditions. And that's it. So that's pretty cool. So let's take a look at what this looks like in an IDE. So for that, we have a separate subcommand called BazelDebug adapter. Flags are the same. Otherwise, there's a new bind port address that defaults to 4711. And to do this, I'm going to also have two terminal windows open, one for the server, one for the client, and then we'll look inside the IDE. Before that happens, we need to have a launch configuration for VSCode. This is called launch.json. And this extension Bazel stack VSCode can provide this configuration for you. So let's see what that looks like. Okay, so we're starting our server, blocking, and the debug adapter is now running, waiting for its communication. The debug server port defaults to 4711, so that's good. We're going to start a session. Okay, we're paused at the beginning of the file. Now the ergonomics of setting breakpoints is a lot nicer, obviously in the IDE, so we can just set a breakpoint, line 154. Let's continue. Now we've hit the breakpoint, we're paused at that point, and we can step through and we can watch this platform flag being constructed and the settings dictionary updated and the rule transition sort of effectively occurring. So that is it. That is a rule transition in Bazel, and it's pretty cool. We can see it happening in the debugger. So it's taken me a while, but I actually do like this experience. What I typically do is just leave this BazelDebug adapter running in a terminal. And if something surprises me or if I get confused by something, I'll start a quick debug session after doing a little bit of research beforehand to kind of see like where I'm interested in. That's it. So I do have a few debugging tips for you at the end. One is simply don't hesitate to make changes within your external output base. I do this all the time. Like for example, here I'm putting a print statement inside Gazelle because maybe Gazelle is running for too long and I don't understand what it's doing. So I'll just go into that directory. Maybe I'll open up a different IDE window and make changes. So that can be very helpful. The next is -- subcommands. This is useful for printing the command lines for the actions that are spawned by Bazel during your build. And that pairs nicely with -- sandbox debug. And sandbox debug will prevent Bazel from tearing down or removing all those symlinks and files in the sandbox. So you can change directory or CD into it and do a postmortem, try to figure out why the action isn't working. There's also -- client debug. Client debug's a bit more esoteric, but it does tell you events that are occurring inside the front end, which is written in C++. And then finally, -- experimental UI debug all events shows you messages coming across the event bus. And I find this interesting because it prints both when an action starts and ends, which is information that's kind of hard to get otherwise. Okay, finally, if all else fails, you can attach a Java debugger to the Bazel server using -- host JVM debug. Here's a sample launch configuration to do that. Good luck. And yeah, that is the debugger as the debug experience. Hopefully you learned something, and hopefully you'll learn something in the future using this kind of tool in the future. Don't hesitate to reach out. I'm PCJ at StackBuild, and I'm PCJ on GitHub. These are some of my other projects. And thank you very much.